Hello everyone, so our presentation will be focused on KMP algorithm using prefix function. The substring search method deals with the problem of which we were given a text string of length n and a pattern of length m, and we are to find out where the pattern exists in the text. It is extremely important in our daily life, ranging from our use in PDF or doc to search for certain pattern words, or more complicated topic modeling in machine learning. So an obvious method is to use brute force substring search, of which it checks each possible position in the text at which the pattern could match. Yet it requires around n m characters in the worst case, which could happen in situations like when text and pattern are all A's followed by a B. And so the brute force algorithm is not efficient due to its back into the beginning every time we find a mismatch, ignoring the previous check. Therefore, computer scientists developed this KMP algorithm that takes linear time, of which its worst case running time is m plus n, and it's more convenient to use on an input stream of undetermined length. In the class, we learned about one case within KMP with DFA. In this method, we never back up the text pointer I and use an array to record how far to back up the pattern pointer j when a mismatch is detected. But now we want to introduce KMP with prefix function, of which I will pass on to my colleague Meng Xuan.
Thank you, Claire. First, let's have a look at what the prefix function is. Basically, given a string s, the prefix function is to construct an array pi of equal length, where the ith entry is the length of the longest proper prefix, which is also a suffix of the substring of s from 0 to I. For example, consider string ABBAB. AB is the only prefix that is also a suffix, so the length is 2. In our constructed array pi 0 is equal to 0 because substring of s from 0 to 0 is a single character string, and we say that the proper prefix of the string is a prefix that is not equal to itself. Now we have pi 0, and we're going to use it to construct the other entries in pi. Before we do that, here's an important property we must know about the array pi. The I plus 1's entry must be less than or equal to pi I plus 1. Look at the example. If we have the i's entry to be 4, s0 to s2 should be equal to si minus 2 to si. That means that the pi I should be 3 instead of 2. That's a contradiction, and that is why we have this property. Now back to the construction of pi. To find the I plus 1's entry, we use the idea of dynamic programming, where we assume we have pi I. If we have the next character of the prefix and suffix to be equal, we can increase the length by 1. So the I plus 1's entry is just pi I plus 1. But if they're not equal, we hope that we could find a shorter prefix that is also a suffix, shorter than pi I. Assume the length is j. Look at the illustration here. J is a prefix that is also a suffix of substring of s0 to si. We can move j to the very front because we have the same pi I at the front at the end. If we move j to the front, j is the prefix and suffix of substring of s0 to s3. So we can let j to be pi I minus 1 and test if sj is equal to si plus 1. If they're equal, then we let the ith entry of pi to be j plus 1. If not, we just continue this process until j is equal to 0. This slide summarizes the process I just described. Next, let Adam demonstrate how prefix function can be used in KMP.
As my partner Claire mentioned before, KMP wants to avoid backup, which was the problem with the brute force algorithm. DFA and prefix functions are just two different tools to achieve that. I will illustrate with an example. Here we have a text and a pattern, and the first three characters in the pattern are matched, but we have a mismatch in the fourth character, so we need to start a new search. But where do we start? If we're using a brute force algorithm, we'll go back to the second character in the text, which we already examined, and start matching it with the first character of our pattern. That is clearly a backup, and that is clearly a waste of time. We want to stay at the current position in the text and just move the pattern to the right. How far we move the pattern depends on if there's a suffix of ABC that is also its prefix. This is where the prefix function kicks in. Clearly, ABC does not have a suffix that is also its prefix, so we have to move the pattern all the way to the right. Here is an example where we do not need to move the pattern that far. The first 6 characters in the pattern are matched, but we have a mismatch at 7. We need to move the pattern to the right. So we look at ABCDAB and see if it has a prefix that is also a suffix. We can see AB is 1. And that is how we move the pattern 4 characters to the right and continue matching. Note, and this is very important, that we never go back in the text to re-examine any of the characters.
Here's a demo of constructing prefix function. Pi 0 is 0 by definition. For pi 1, now j is pi 0, which is 0. We compare sj and si, they're not the same, so pi 1 is still 0. Same for 2 and 3. Now for pi 4, things are different. Sj and si are the same, so pi 4 is now 1. Again, same for 5 and 6. Now for pi 7, this is the tricky part. Sj and si here are different, so we try to find a shorter j by making j equal to pi 2, so j is now 0. Compare sj and si, they're the same, so pi 7 is 0 plus 1, which is 1. And this is a demo of KMP using prefix function. We start at the first character in the text, and we have matched the pattern until the very last character. Now we look at the prefix function 1 entry before. We have 2, so we move the pattern right and compare the third character of the pattern with A, the current character in the text. This is the basic process. We continue matching if the characters are the same, and if we have a mismatch, we look at the prefix function and decide how much we want to move the pattern right until we finally find the pattern.
Thank you, Mengshuan. So now we'll be presenting the code and analysis for the KMP algorithm using a prefix function. The algorithm is split into 2 parts. The first part we will look at is the function that generates the prefix array. Note that it only takes the pattern as its input. It begins by initializing the array that is +1 the length of the pattern length. It also initializes the default cases of the first 2 values that are -1 and 0. We then loop through the characters of the pattern string in the while loop, incrementing our pointers when the characters match in the first if case. If they don't match, we reset our prefix len to the appropriate value if we're in the case that we were onto a match in the second case, or other words, our prefix len was greater than 0. And in the third case, we iterate our pointers and move forward given that our prefix len is equal to 0. Note that if we only iterate through the while loop once, thus resulting in O of m time complexity. Now we have the main algorithm. It begins by initializing the pointers we need as well as our resulting matching array. It begins by generating the prefix array and iterating through the entire text string. It then starts making comparisons based on the pointers. If we have a match, that is the first case, then we iterate our pointers forward. If it happens that our match is at the end of the pattern, we then add our resulting match and reset our p pointer as seen in the nested if. Else, we move our pointer forward according to the prefix function. Since p is at most rolled back as much as it progressed up to the mismatch, and the while loop only runs once, it runs proportional to the length of the text, or O of n. Moving on to the analysis, the runtime of the whole algorithm is O of m plus n, where m is the pattern length and n is the text length. The prefix function generator, as shown, only iterates once, or some multiple of the pattern length, resulting in O of m time. The KMP algorithm, ignoring the table generation, as shown before, runs in O of n time as the text pointer never moves back as a result of the prefix table. Combining both, you get O of m plus n time. In terms of space complexity, it runs in O of m space, including the solution which will store some multiple of the pattern and the prefix table, which takes m plus 1 space. Something else to note is that the prefix function runs in a similar time to NFA, or a non-deterministic finite automata. A DFA is actually a special case of an NFA. Here are our references, and thank you for listening to our presentation.